Hello. So in this video, we're going to be talking about horizontal asymptotes. And actually, we're going to be sort of revisiting some stuff about asymptotes in general that you may have heard or learned in prior courses that sort of, especially in calculus, can be a little misleading. So to start with, sort of to motivate the idea of horizontal asymptotes, and we'll see how this motivates in a minute, but in general, this idea of Nterm behavior can be sort of a very useful thing to know about. And in fact, we have done this, you should have done this at least in things like precalculus and maybe even algebra 1, algebra 2, when you're looking at how to do curve sketching and understand how sort of functions behave as they get sort of toward their larger and larger input values, okay? So these Nterm behaviors, which, as we're about to see, is pretty much the same thing as a horizontal asymptote. So when you learned it as Nterm behavior, usually the way it's introduced is this idea of what does the function do when the input gets very, very large, right? At this point, though, now that we have limits under our belt and we understand sort of what limits are, this should sort of be pretty familiar, right? In fact, when we did limits at infinity, this is exactly that kind of idea. So we can actually reframe this question now in terms of our limits mechanics. So really what this question is asking is, what is the limit of the function as the input goes to infinity, okay? So in general, when you have done asymptotes in the past, they have almost certainly sort of had this, again, almost Pavlovian reflex of telling you, right, that asymptotes are lines that functions can't cross. This is usually the tagline for asymptotes. Unfortunately, this is not at all correct. You don't want to remember this. This is, in fact, not just incorrect, but it's almost exactly the opposite of how you want to think about asymptotes. Asymptotes are not these things where they're barriers that the functions can't cross. In fact, functions can cross asymptotes of certain types, and we'll see that very shortly. A better way to think about it, though, is that asymptotes are lines that sort of pull in functions. Okay, so they are these barriers in the sense that they're sort of trying to attract the function to get as close as they can to becoming what that line is doing. So it's if it's a vertical line, it's going to try to pull in the function to look as vertical as possible. If it's a horizontal one, it'll try to pull the function into looking like a horizontal line. Now, to be clear, vertical asymptotes, these are domain restrictions inherently, and we'll talk about that very, very soon in a whole bit about vertical asymptotes. But because they're domain restrictions, they can't be crossed. So it's not that it's a vertical asymptote. It's not that it's an asymptote, and that's why it can't be crossed. It's because it's a domain restriction. That's the problem. But horizontal asymptotes, for example, and you may have heard of other ones which we're not going to be discussing in this video, like slant asymptotes and things like this. Those other ones absolutely can be crossed. And in fact, they can be crossed infinitely many times. So let's look at an example here. So we have this graph, and it's sort of this weird squiggly looking thing, right? And in fact, as it goes sort of off to the right and left, it sort of gets damped down, right? It gets sort of less squiggly, I guess, as we go, right? So we can sort of write out, sort of record where this thing is getting sort of damped down into, and we can see this sort of dashed line here. This is going to be the horizontal asymptote. So as it goes and becomes bigger and bigger x values in the right or the left direction in this case, the function is getting sort of crushed down to become more and more and more horizontal as it goes. So this dotted line represents a horizontal asymptote. But also clearly, right, we're crossing this thing all over the place, right? There's all kinds of crosses here. And you might think like, okay, but like Nterm behavior is just for really, really big x values. Maybe it's the fact that, you know, it's only crossing nearby. But in this particular case, with the function that this graph represents, this thing is going to be crossing it infinitely many times, no matter how far you go away. So you can definitely have functions, and actually they're not that uncommon, where it crosses these asymptotes, okay? So this line that we have here, right, this is our horizontal asymptote. But we want to sort of bring this back to the idea of limits, right? That's the goal. It's like, now we have this idea of limits, what's going on? So remember that a limit is a value your function gets closer and closer to, and that's how it sort of becomes a limit, right? It traps it near this y value, right? So if you remember when we did limits at points, we did like left and right limits, and we had to show that they went to the same place because they had to get infinitely close to each other, right? They had to get sort of exactly to the same spot. So that's essentially what we're talking about here, right? We have this line, and the claim is, right, what I'm saying is that horizontal asymptotes represent what it tries to make the function turn into, meaning that the function is trying to become exactly this line, is trying to get pushed down to be as close to this line as possible, which means that we're doing exactly the same thing here, right? The limit of the values getting closer and closer to is also the same role for the horizontal asymptote. Now, the one rub here is that the asymptotes are lines, right? So an asymptote is this collection of points, whereas a limit typically is a point, right? We usually say the limit's value is 5 or something like this. But that's why we're doing this sort of slightly different variation on a limit, which we talked about before. So these are limits at infinity. So remember, right, in our limits at infinity video, we talked about how the limit at infinity isn't really a limit at a point. It's this sort of abusive notation is what we call it, but it's basically a shorthand for a limiting behavior. What's it doing as the input is getting bigger and bigger, right? So it's not a value at a point, it's behavior as that limit gets larger and larger and larger. Now, in the past, almost always when looking at horizontal asymptotes, and this is true if I go back real quick here, this is true right here as well, that the left and right sort of behaviors are mirror images, right? This horizontal asymptote is the same asymptote left and right. And this is for a variety of sort of pedagogical reasons in the past, given the sort of restrictions that occur when you don't have limits. Fortunately, or unfortunately, depending on your perspective, we now have limits, and so we can talk about left and right horizontal asymptotes. Now, to be clear, usually when these things are discussed, they're not specified. So if you look at it in a book, they won't say like right horizontal asymptote or left horizontal asymptote. They'll just call them horizontal asymptotes. Nonetheless, it's useful to think of it this way. So looking at the classical sort of exponential function is a good example of this. If we think about what this thing looks like, it's sort of, the Superman function, right? It goes up, up, and away in one side, but the other side sort of keeps flattening out as it goes over. And so if we think about taking a limit at positive infinity, it's going to get infinitely large, right? It's going up, up, and away. But if we look at going to the other direction, if we look at going for x to the negative, we are approaching horizontal asymptote, right? And in fact, they mention this in precalculus, and it's easy to sort of miss in the sort of large amount of information you're getting on all the different parent functions. But nonetheless, sort of important for our example here, this would be an example of what you might think of as a left horizontal asymptote. It only applies in one direction. So moving forward, it's important to note that there are examples of functions, now that we have limits, that we can give you where the left horizontal asymptote and the right horizontal asymptote may not be the same. If you have different ones, usually they're just listed. They'd say, okay, there's a horizontal asymptote at 2, at y equals 2, and a horizontal asymptote at y equals 7, or something like this. And usually what that means is that one of them is a right and one of them is a left, and you have to figure out which one's which. So it's a little annoying, the fact that we don't specify, but that's the standard convention, okay? So just to sort of make official recap what I was just saying, when you're taking limits of your function, as you're going to infinity, you want to look at both positive and negative infinity to find horizontal asymptotes. So for positive infinity, we use this notation, if you remember from our limits at infinity section. So this would be looking at what we might think of as the right-hand horizontal asymptotes. And likewise, the negative side or the left horizontal asymptotes. To be clear, it is very common for a lot of very interesting reasons that you will get the same horizontal asymptote in both ways, like going in both positive and negative, but that's not always the case, so it is important to check. Okay? So what do we talk about? So limits at infinity and horizontal asymptotes, these are basically the same thing, right? They're both asking, okay, what is the function sort of behaving like or doing as we get infinitely large values, positive or negative? So in many ways, these are sort of identical ideas. Context can make it sort of more useful or more obvious which one we might want to talk about, but they are, for almost all intents and purposes, basically the same idea, okay? Big takeaway here that sort of is unlike maybe your previous exposure to asymptotes is this idea that asymptotes, they're lines that try to pull functions in and trap it nearby. So they aren't things that the function can cross. They're things that are trying to sort of mimic what the function is trying to do, or trying to force the function to do a very specific thing, try to become that line. And this is true for any kind of asymptotes: vertical asymptotes, horizontal asymptotes, slant asymptotes, asymptotic curves, if you've heard of those. Like all of these things, that's what it is doing. It's trying to get the function to become that asymptote. And finally, the mechanical takeaway here: in order to compute horizontal asymptotes, right, you have to do the limits at infinity, but you do need to make sure you check the positive and the negative directions, because now we're sort of far enough along that we can have functions that have sort of either of those options could give you horizontal asymptotes, and in fact, they could both give you horizontal asymptotes, but have them be different things. So you do need to check them both, okay? So that is that.